thing now. So,
Sir, I'm going to finish up it after then since you're gonna start the class.
okay, no problem. All right, so here we are now. We're going to be looking at this thing which we, well, let me just kind of set up the topic instead of just jumping right into it. So, we're going to be looking at a very foundational concept, right, when it comes on to the behavior of materials, right, and materials of a specific nature, right? Because we can think about situations, where we, for instance, we get a, what do I want to do? All right. For instance, we get a, let us say, for the females, they might get a scrunchie, right? Or one of those thing that they used to, put the hair in a bun. So you might get one of those and you will realize that, when you just get that scrunchie or whatever you guys call it, you're going to realize that, when you're using it, for instance, to catch up your hair, you're going to realize that once you stretch it, right, it tends to return to its original shape or original length. But what you're going to realize that over time, that ability for the material to return to its original length will actually reduce, right? So it's not going to have that elasticity as it had once it was brand new. And we also see the same principle when it comes down to things like elastic bands, springs, right? We see where after time, based on how much that material has been stretched, we will realize that it will not return to its original shape. And also, we can visualize or imagine when we have an elastic band, the more we pull on it, the longer it gets. So the more we pull on an elastic band, or in other words, the more force we apply, the longer it gets. So what we're going to be looking at today is we're going to look at a concept related to that. Right? So we're going to get into dealing with that right now. So what we're going to talk about is a thing called Hooke's law, right, which was developed or which was studied by a scientist back in the 1800s by the name of Hooke, right, naturally. So Hooke's would have, well, his name is Hooke actually, Hooke, and they would have assigned or attributed his contribution by a law known as Hooke's law. So we're gonna be looking at that today. So let's just jump right into it then. So let's talk about this thing called Hooke's law. Right? And we're going to start by just writing a definition for Hooke's law. And again, as I said, Hooke's law deals with materials of an elastic nature. So things like elastic bands, springs, right, can be described using Hooke's law, right? And what Hooke's law says, by definition, let me just start by writing that definition. So what Hooke found out in his experiments is that so let me say that this states that the extension of a spring, right, and it could also work for elastic bands, right, so the extension of a spring, let me also mention, or elastic band is directly proportional to the applied force, right, with a limitation, right, provided right, something holds true. So far what we're saying is that the extension of a spring or an elastic band is directly proportional to the applied force, right? And we're saying, no, provided something holds true. Now, this first statement right here, we can actually appreciate this because, as I would have mentioned in my discussion a short while ago, that when you have an elastic band or one of those scrunches, the more you pull on it, in other words, the greater the force that you apply to it, the more it will stretch. Is that the case that you guys observe?
Yes, sir.
Okay. All right. So that's Hooke's law. So it says that the extension of a string or an elastic band is directly proportional to the applied force, provided the proportional limit is not exceeded. Okay? Any question on this so far?
No, sir.
Okay, so that's Hooke's law. Jonathan?
Yes, Junior?
Yes, all is well?
Yes, I just lost track of time.
Okay. So we're talking about Hooke's law, and we're saying that Hooke's law deals with materials of an elastic nature, so things like springs, elastic bands, right? They can be described using Hooke's law. And what Hooke's law says is that for a material, its extension will be directly proportional to the applied force, provided that we have not exceeded the proportional limit. And we're going to talk about this proportional limit as we go further in our discussion. So that's Hooke's law by definition. Now, if we notice in our definition right here, we said something is directly proportional to the applied force. So we're saying that the extension is directly proportional to the force. So we have extension being directly proportional to the applied force. So once we say extension is directly proportional to the applied force, we can make a mathematical statement, right? So that mathematical statement we can write is we can say, okay, our force F is directly proportional to the extension E. So we get F is directly proportional to the extension E. Now, during his experiments, Hooke, right, and let me just put his name on the screen. His name is Robert Hooke, right? That's the name of the scientist who studied this phenomenon right here. Now, what Hooke determined in his experiment was that there is a constant, right, that is specific to that material. So for any given material, we can write F, which is the applied force, is equal, as because again, once we change our directly proportional sign to an equal sign, we introduce a constant, and that constant was called K, and I'm going to tell you exactly what K is shortly. So we have F is equal to K multiplied by E, where K is some constant, and that constant is specific to the material. So we get F is equal to Ke, and this expression right here is what we use to summarize Hooke's law. So Hooke's law can be summarized by this expression where we say F is equal to Ke, right? So F is equal to a constant K multiplied by the extension. So let's just outline what these variables represent. So F is the applied force. So let me just say the force applied, or applied force, whichever. So the force applied, right? And this force is measured in newtons. K now is what we call the spring constant, or generally speaking, it's called the stiffness constant. But since we're going to be most times dealing with springs, we say that it's the spring constant, right? Spring constant. And we're going to talk about the unit for the spring constant shortly. And E now is the extension, right? Extension, and it is measured in meters. Now, sometimes you might see this expression be written as F is equal to Kx. Same thing, right? We're just using X as the extension, right? So you might see it as F equal Kx or F equal Ke, right? E is just the extension. Cool?
Yeah, I get it.
Okay. So that's Hooke's law. Now, let's talk about, okay, what's going to be the unit of the spring constant. So let's say we were to make k the subject of this expression right here. So we're going to make k the subject. So if we have f equals ke, how could we make k the subject?
So divide both sides by
Huh?
so divide both sides by e.
Divide both sides by? Okay, so we divide here by e, divide here by e. So e cancels with e on this side, and we can put k on the left, so we have k is equal to f over e. So k is equal to f over e, and f we said is the force measured in newtons, and e is the extension measured in meters. So therefore our unit now for k becomes what?
Newton per meter.
Newton per meter, n slash m, right? Or we could write it as nm to the minus 1 because this is in the denominator. So it's Newton per meter or Newton meter minus 1 to the minus 1. So therefore now our spring constant, the SI unit is Newton per meter. Or again, we can write it as nm to the minus 1. So that would be your unit for the spring constant is the Newton per meter, which we can write as n slash m or nm to the minus 1. So that's that's Hooke's law. So Hooke's law again says that the extension is directly proportional to the applied force, provided that the proportional limit is not exceeded.
So you can just roll up please.
Now, once we say
Take a screenshot.
the extension is directly proportional to the applied force, what we simply mean is that when we increase the force, right, we're going to see that the extension will also increase, and they increase by the same factor. So that means doubling the force results in the extension also being doubled. So the more force you apply, the greater the extension, right? Less force you apply, the smaller the extension. Now we can also show this law right here, Hooke's law, using a graph, and I'm going to consider two types of graphs or two possible graphs dealing with Hooke's law that we can come across. So let me now go into that. So let's say we consider these two graphs right here, and then we're going to look at some examples. So let's say we have one graph here. Say that's one of our graphs. Let's say another one here, next one here. So we're going to consider two graphs, and let's say this is our x-axis, this is our y-axis, and let's say we have force measured in newtons here, and for this one now we have extension, and this is measured in meters. While for this graph now, this is our x-axis, this is our y-axis. On the x-axis, we're going to have extension for this one, measured in meters. And then for this one, we're going to have force, and this is going to be in newtons. So we're going to consider these two graphs right here. Now, let's say, so since we say that the extension is directly proportional to the applied force, provided the proportional limit is not exceeded. So what this statement says, or what this statement means right here, where we say provided the proportional limit is not exceeded, what this is telling us is that once the proportional limit is exceeded, the extension and the force will no longer be directly proportional to each other. So what we're saying is that if we go beyond the proportional limit, Hooke's law is no longer obeyed. And we can show that now on our graph where we say, okay, so since we say extension is directly proportional to the applied force, Sharon, once we say something is directly proportional to something and we plot a graph, how would that graph look? Could you describe that graph for me?
Sir, the line will start from the origin and go straight across.
Repeat, I did not hear you. Repeat.
So the line would start from the origin and go straight across.
Go straight across, so it will go what? Horizontally across? Go horizontally across.
No.
Okay, how would it
I think
go?
it's. Sorry, I'm trying to remember what
Go
it
the
is.
diagonal.
Diagonal, right? Diagonal. It's gonna go
Yes.
diagonal, right?
Yes.
So let's show that now. So we're gonna start at the origin right here, and we're gonna go diagonally, right? So let's say up to like that. But again, as we said, we can reach a point where Hooke's law is no longer obeyed. And as we said now, Hooke's law is obeyed when the extension is directly proportional to the applied force. So what we're going to see now is that beyond a certain point, which we call the proportional limit, Hooke's law will no longer be obeyed. And our graph will look something like this. Let's just continue. Our graph is going to look something like so. All right, it's smooth out. Let me try to do this a little better. Our graph will look something like this. I don't like how that one look. Graph will look something like so. Alright. It's supposed to smooth it out, but yeah. Alright, so let's say like that. The graph will look something like this. Right? So our graph will look something like this. So what we're gonna see now is that with a small force, we get a relatively large extension. Let me see if I can. So with a small force, we get a relatively large extension. So our graph looks something like so. Right? Taking some time to smooth. Alright, anyways, let me just do it as it is. So the graph looks something like that. Right? So up to a certain point, we have the extension and the force being directly proportional to each other. Then beyond a certain point, we no longer see extension and force being directly proportional. Okay? So this is the graph that we will get when we plot a graph of force on the y and extension. So this is a graph of force versus extension. So let me just make a note. This here is, use this color, or this one. This is force versus extension. So this is a graph of force versus extension, and we get this characteristic graph, right, for force versus extension when we plot a graph of force against extension and we exceed the proportional limit. Okay? Now, in terms of our graph here, which is extension against force, what we're going to see is that we're going to get also extension and force being directly proportional to each other, right? Kind of like this, right? But there's going to be a point where the extension and the force are no longer directly proportional. And we're going to see that our graph will look something like this. Something like that. Right? So the graph will look something like this when you plot a graph of extension against force. So we also see now that with a small force, we get a relatively large extension. Let me see if I can make this a little more better. Right, something like that. So with a small force, we get a relatively large extension. So let me just remove some of this at the top. So this graph right here is extension versus force. And we're going to be looking at a graph of this today. Extension versus force. All right, so that's our graph. Okay? Any question? Do we have any question?
You said it was exceeding its proportional limit, right? So why is it bending and not like dropping?
Okay, so very good question. So because the spring was stretched beyond its proportional limit, what we see is that the extension on the force will no longer be directly proportional, right? So what we see now is that the extension on the force will be proportional, but they won't be directly proportional because the proportional limit would have been exceeded. And that is why we see that when we apply a small force, we get a very large extension, right? Because the extension and force are no longer directly proportional to each other. So with a small force, we get a very large extension. Are you with me?
So you're saying that at first it's directly proportional, but when the when it can't extend anymore, it just becomes proportional and not directly proportional.
Okay, well, not necessarily when it can't stretch any further. What happens is, yes, when we just start to apply the force to it, it's going to be directly proportional. And within that region, where it is directly proportional, we call that the elastic region, right? Well, not the elastic region, the proportional region, my bad. The proportional region. Now, outside of the proportional region now, once we continue to apply force to the spring, what we're going to see is that, okay, let us say, let me just put some values right here. Let's say when we apply a force of 5 newtons, we get an extension of, let us say, 2 meters, just for argument's sake. Then when we apply a force of 10 newtons, because we're in the proportional region, and within the proportional region, the force and the extension are directly proportional. So since we double the force, we expect the extension to double as well. So we might get 4 right here. Then now let us say now we go up to 15 right here, right? We're gonna expect to get let me just move this up a bit. Let me undo this. And again, once we plot a graph, we will actually see this to scale. So this is our force right here. So what we're saying now is that we're going to apply a force of, let us say now 15. Let me just put it a little further down. Let's say 15 newtons, right? And we get an extension of, let's say, I still want to have this based on how my graph is. Let me just kind of try a thing with this. Let me try it this way. Spare me a second. All right, let's say this is 5 right here, and we get 2. Then we go to 10, double it. So the extension doubles as well because the force and the extension are directly proportional. So whatever factor we increase the force by, or one quantity by, the other quantity will also increase by that same factor. So let's say now this is 15. So we're going to expect to get this being 6, right? Then now, when we go to 20 now, let's say 20, we're going to expect, let us say this is 8 right here, just on the mark. Then now, when we go to, let's say this is now 25, so I have to move, let me move this up. So we'll go to 25. But what we see now is that the extension, right? Let's just say, let me just kind of show it using some broken lines. So let's say we start our extension right here, which is at 25. Then we go straight across horizontally, right? Touch the graph. Then we go straight down. So what we see now is that the force produces a very large extension. Because, I mean, if we were to continue going up by the same increment, this might be 10. This might be 10 right here. And this might be you know, probably, let me just say 10. Just is a sketch, so that's 10. Let me fix this. So this could be 10 right here, and this could be, let's say, just say 12, for example. So notice, when a force of 20 newtons was applied, right here, the extension was roughly 8, right? We could say that?
Yeah.
Right? Extension was roughly 8. So if we go across like this, the extension was roughly 8. If I can just get it perfect, let's just say, or just like that, the extension is 8. Now, because we're no longer within the proportional region, we see that when we increase the force by 5, look how much the extension increases. The extension increases by 4 in this case. So all this time, when we apply a force of 5 newtons each time, the extension was 2. Because when we were at 5, the extension was 2. When we go to 10, it was 4. So each 5 newtons we add, the extension increased by 2. But in this case now, when we increase the force by 5 newtons, we get an extension of 4. So what we see now is that they are no longer directly proportional to each other. Okay? Because a small force produces a very large extension. Are you with me?
So so you have your proportional limit, right? What did you call it? The area where everything was proportional.
Right, I'm going to label it up right here. So let me label this up. So this right here would represent our proportional limit. Let me just label it with an arrow. So this is our proportional limit. Right? And this now, from our proportional limit straight down, right? This is going to be our proportional region. Region, right? And within the proportional region, Hooke's law will be obeyed. Outside the proportional region, Hooke's law is no longer obeyed, right? Now, there's also another point on the graph that we want to establish. Right, let us say right here, let's just say I put it right here. This point right here is what we call our elastic limit, and I'm going to be defining these terms shortly, the elastic limit and the proportional limit. Okay?
Yeah.
Okay.
Understood.
All right. So that's that, and we can also define the same over here. So let me just do it over here as well. So here will be our proportional region. Right? This right here would be our proportional limit, my bad. Proportional limit. Right? And just slightly outside of the proportional limit, we're going to have what we call the elastic limit. Right? So those are our two possible graphs that we can obtain once we plot a graph of force. Well, we could plot a graph of force versus extension, or extension versus force. Okay? Now, generally speaking, because oftentimes we will come across a situation where we might be required to find, from the graph, we might plot a graph of either force versus extension or extension versus force, and we might be required to find the value of our spring constant K. Now, what we're going to see now is that if we plot a graph of force versus extension, we're going to see that our gradient, whatever value we get for the gradient within the proportional region, will be equal to our spring constant. So the gradient then now will be equal to the spring constant once we plot a graph just like this one. However, if we plot a graph of extension versus force, our gradient will be equal to what we call the inverse, or 1 upon the spring constant. So what we'll have to do now is we'll have to transpose our formula in order to find the value for the spring constant. Let me just write this a little better. Otley. All right, so that's that. So let's continue. So now that's our two graphs. So let's talk about the proportional limit. Proportional limit. All right? So the proportional limit. So what we're saying now is that this is the point beyond, well, let's say the point at which so let me phrase it this way. So the proportional limit is, as I said before, it's where Hooke's law, if we go beyond the proportional limit, Hooke's law will no longer be obeyed. So we can say that this is the point at which, if more force is added, the extension is no longer directly proportional to the applied force, and hence Hooke's law is no longer obeyed. So once we would have exceeded the proportional limit, Hooke's law is no longer obeyed. All right, Hooke's law is no longer obeyed. O-B-E-Y-E-D. Does that make sense? Are we making sense here?
Yeah, so basically the proportional limit is where it's like, say Hooke's law is a box, and the proportional limit is everything inside the box. So the stuff outside the box isn't Hooke's law doesn't apply basically, right?
Right, exactly. All right. So that's the proportional limit. Now we can also talk about what is called the elastic limit now. So let's talk about that one. So we have the elastic limit. Right? Now the elastic limit now, it is very specifically defined. So let's consider it now. So we're going to say that this is the point beyond if this, well, let's say the point beyond where if we extend or stretch the spring beyond this point, what we're going to see is that the spring will lose what we call its elasticity, or in other words, it's going to lose its ability to return to its original length. So we're going to say now that this is the point beyond if more force. Let me phrase it this way. I want to phrase it in such a way that it makes complete sense. So let's say now that this is the point. Let's say this is the point. Let me use the same wording up here. Let's say this.
So you can say this is the point at which.
Right, yeah, that's what I'm saying. I'm going to use the same phrasing right here. This is the point at which, if more force is added, the spring loses its ability to return to its original length, and in this case now, we say that the spring is, what's the D word we can use to describe a spring that, or a material that does not return to its original shape? Huh? We're starting with D. D what? Huh? Right? So we say that the spring is deformed. So once we would have exceeded the elastic limit, the spring will now become deformed. So that simply means is that it will not return to its original length. Alright, so let us say we have a spring of a particular length, let us say 5 centimeters, and we apply a weight to it, and it stretches. And you guys would probably see this before, because you know, sometimes you have a spring. Let's say this is our spring right here. Let's say this is the spring, right? Let's say that's the spring. Now let us say, you know, we could stretch this spring, and when we stretch the spring looks something like this, right? And no matter what, it will never go back to this original shape, because it would have exceeded the elastic limit. Okay?
Understood.
Okay? And what you're going to realize now, if we continue to apply more force to the spring beyond its elastic limit, in other words, way beyond its elastic limit, what could happen to the spring? All right, think about an elastic band. If
Wouldn't it snap?
it will snap, right? Or in other words, it will break. So it will actually reach to what we call its yield point or its breaking point. But we don't necessarily consider those, because even when we do experiments, you know, we always ensure that we don't go to the elastic limit, at least, right? And if you notice on my sketch right here, that I show the elastic limit and the proportional limit to be very close to each other, right? Because they're very, very close to each other. And you're going to see that in some textbooks, they might define Hooke's law, where they say the extension is directly proportional to the force, provided the elastic limit is not exceeded. So you might see defined that way, but more accurately, it is really the proportional limit, because what you're going to see, as I said before, is that the spring is the extension and the force are only directly proportional up to the proportional limit. But again, because the elastic limit is so close, right, oftentimes, you know, it is considered to be up to the elastic limit, right? So just wanted to put that out there so you guys are aware of that. Okay? Are we okay with that? So let's move on to our lives. So let's try some examples. So let's say examples. So we're going to try some examples here. So let's try some examples. Let's say, all right, hold on a second. By the way, anyone have any questions on this? Any questions?
No, sir.
Okay. All right. So we're going to work some examples. Give me a second, please. Let me just send out this message. All right. So let's try some examples. So let's say a spring has a spring constant of, let's say this is 200 Newton per meter, calculate the extension, or let me say calculate the force needed to extend the spring by, let's say, 0.25 meters. Let's just say that 0.25 meters. So the first thing we do is we write our formula. So the formula says that the applied force F is equal to KE. So F is equal to KE. So that's our formula. Now in our case now, F is unknown. The spring constant K is given as 200 Newton per meter, and we are told that our extension E is 0.25 meters. So once we have all these variables now, we can consider our expression. So since we're trying to find the force F, we can just substitute the values in. So K is 200 Newton per meter, and we're multiplying that by the extension, which is 0.25 meters. So all we have to do now is to just plug this into a calculator, and when we do so, what's the value we get? Right, 50 newtons. Right, 50 newtons. Right, so we'll just multiply this together and we get 50 newtons. Anyone have any question on this? Any question?
What if you're trying to find the extension?
Okay, let's try an example like that. Let's try an example like that. Let's say calculate the extension of a spring. And let's make this a two-part question. Let us say calculate the extension of a spring of length. Let's say its length is 0.4 meters, right? So it's let me just say 0.04. Let's say 0.06 meters. Let's just say that 0.06 meters. When a force of, let's say a force of, could somebody give me a number?
Let's see, 150.
150, all right, 150 newtons is applied to it if its spring constant, let's say this is 250 Newton per meter. Let's see this. Let's see what happens here. All right, let me just put another 0 on this. Let's say this is 2,500. Let's see how things work out here. So 2,500 newtons per meter. So let's see what we have here. So first of all, let's write out our formula. So the formula is F is equal to KE. Now we're given the force, so we're given F as 150 newtons. We're given K, and we said that K is 2,500 Newton per meter, and we want to find the extension E. So let's work that out now. So let's say, so first thing, in order to find E, we have to make E the subject. So we have to transpose our formula, so we have E being the subject, and how would we do that? Divide both sides by K. So we divide this one by K, divide this one by K. So what we're going to see is that K cancels with K. So we're left then now with E, which is the extension, is equal to the force divided by the spring constant, K. So let's now evaluate this now. So let's say we go here. So this now becomes 150 newtons divided by 2500 Newton per meter. And anybody calculated a value for this? What are we getting for this? What do we get for this?
0.06.
Okay, 0.06, and this is meters. So the extension
Yeah, meters.
0.06 meters. Is this okay? Right. Let me just change this value right here. Let's say this is initially I was thinking 4, so let me just put 4. So let's say that's the question right here. So this right here represents the extension E. Okay? Now let us say we want to also find out, let's say we want to find out what is the new length of the spring. So how would we find the new length of the spring? Huh? If we had a
Would the new
0.
length of the spring
Repeat.
be the extension?
Repeat for me?
Would the new length of the spring be the extension?
No.
Then would you subtract the extension from the spring of length?
Original length? Well, not quite. Let's look at it. Let's look at it. So let's say this is our spring attached to some fixed object. Let's say this is the spring originally, like that. Let's say this is it, right? Now, when we attach the force of 150 newtons, let's say the spring now looks like this. Let's say that. Right? And this is our 150 newton here. Let's say like this, 150 newtons. So originally, right, the spring would have a length which we can represent as this right here. Let us say this was what? 0.04 meters. Now we're saying now that the spring had an extension, and let me just put the extension right here. Let's say the extension,
So you would add the extension to the spring of length.
the original length of the spring, right? So this would be 0.06 meters. So what we see now is that the new length would be from here, go all the way down to here, which is just the sum of these two, which would be 0.06 plus 0.04, and you're going to get 0. Let's say 0.10 meters. Okay?
Understood.
Now, that allows me to just share with you an expression for the extension. So the extension, E, is given by the final length, let's say L, F, final length, minus the original length, L, O. So the final length, extension, sorry, is equal to the final length minus the original length. Now, from this now, we can make the final length the subject by simply, let me just write it down in the next line. So we have E is equal to the final length. Let me make some space over here because of how I'm going to write this. So let's say now extension E is equal now to the final length LF minus the original length L0 or L0. So because we're trying to find the final length now, what we can do is we can add the original length to both sides. So we add the original length to both sides, and in doing so now, these two will cancel each other. Right? These two cancel each other, so we're going to have the extension plus the original length will give us the final length LF. So to find the final length, we just simply add the extension to the original length, okay? Are we okay with that?
Yes.
Right? Let's try one example of that nature now. So let's say, example 3, let us say the spring below as
Sorry, scroll up a little, please. Scroll up a little.
here.
Yes.
Right?
Just want to take a screenshot.
Okay. Let's say now the spring below as
You continue now.
a
Can I continue now,
load.
sir?
Okay. A load of, let's say this is 800 newtons attached to its end. To its end. Right? Let me just sketch this out. Let's just sketch this out. So let's say we have our, let's say this is like that. So let me just show this spring right here. So that's our spring. And again, this is some fixed object, like for instance, a ceiling or so. So let's say this is what we have. Now let's say when the spring is like this, let us say its length is, let's say this is 0.16 meters. Doesn't really matter anything, but let's say 0.16 meters. Let's say that's that. All right. Now let's say now we attach a the 800 Newton load. So this is the spring now, like so. Bam, 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 bam. Like so. And this is the 800 Newton load. This we say is 800 newtons. And let's say now that this spring is now, I'm going to say 0.24 meters. Let's say that's what we have. And our objective now is to, let me add it right here. Objective is to calculate the spring constant K. So we want to find the spring constant K. So we have this diagram right here. First thing we do, write out our formula. F is equal to KE. Now in this case now, we know F, let me put the values right here. F is equal to what? F is equal to what? Huh? F is equal to? Anybody know? Huh? Repeat, I'm not hearing you so well, Sharon. Huh? Could you type what you're saying in the chat? Because I'm not able to hear you, Sharon. In the meantime, anybody else have anything? What's the force? Constant by extension? No man, what's the value? What's the value of the force that is being applied to the spring? What's the value? Based on the diagram, what's the value of the force being applied to the spring?
It says 800 newtons.
Right, 800 newtons, right? So the force F would be 800 newtons, right? So it's 800 newtons. And what's the extension?
0.08.
0. Oh, we got 0.08.
I subtracted the final value from the original, so the final length from the original length, and I got 0.08.
Okay, so the extension again is the final length minus the original length, which is 0.24 meters minus 0.16 meters, and this will get was 0.8 or 0.08.
0.08.
Okay, 0.08 meters. So that's the extension, and we're trying to find k. So k is our unknown, so we need to make k the subject. So dividing this one by e allows us to see that k is going to equal to the force divided by the extension e. So the force now is 800 newtons, and the extension is 0.08 meters, and this works out to be what?
So 10,000 newtons per.
Repeat.
So 10,000 newtons per meter.
Alright, so 10,000 Newton per meter. Are we okay with that?
That's what I got, so
Alright,
sure.
so that's good. So notice when we have no object attached or no force applied to the spring, right? We're gonna see that, maybe I'm gonna ask a question like this. We'll try to work a question like this with you before I give you some examples. All right, so we have this spring right here, and we're saying that there's no force being applied to the spring, so its length, when no force is acting or applied to the spring, will represent the original length of the spring. So because no force is applied, the original length is 0.16 meters. So I was just thinking about a question here. Let me see if I can set it up. Let me just set it up by considering a diagram. So I'm going to see if I can mix moments with this question. Let's see if I can do that. So let's see now. Let's see. All right, let me see something now. So let's see this now. Let's say we have a pivot right here. Let us say this is our pivot. Let's say the pivot is right here. So bear with me for a second. Let me just set this up. So let's say this is our pivot.
Sir, scroll up, please.
Give me a second. Let me just first, and then I'm going to scroll up shortly. So let's say that's our pivot there. And let's say this is the center of this plank, and let's say this plank has a weight. I'm just going to indicate a value. Let's say the weight right here is, could somebody give me a value for the weight of this plank? Huh? Could somebody give me a value for the weight of this plank?
500 newtons.
Okay, all right, 500 newtons. Let's say that's 500 newtons, right? And let us say that we have a spring, and let's say that spring is attached to the end right here. Let's say this is some fixed point, right? And we have, let's say, this spring right here. All right, let's say the spring is attached right there. And let's say that this spring at the original length, let's say L naught of this spring is probably, let us say, 0.2 meters. Let's just say that. Now let's now talk about some dimensions for this plank right here. Let's say the spring is attached to the end of the plank, right? And let's say that the length of this plank is, let's say the length of this plank, let me just put it down here. Sorry, let's say the length of the plank is use a different color. So the length of this plank here is, let's say this represents the length of the plank. And this plank is of length, let's say it's 4 meters, right? 4 meters. So it's a 4 meter long plank, and we have the pivot right there, right? And let's just say the pivot is, let's say from here to the pivot, let's say this is, as I said, I'm going to go through this question with you. Let's say this is, probably 0.8 meters, right? So we have a uniform plank right here, which is 4 meters long. We have the pivot that is 0.8 meters from one end of the plank, and we wish to say, let us say we want to find out, okay, what is the force applied to the spring. Let's say we want to find out the force applied to the spring. So let's see now. So let's say question 1, we want to calculate the force applied to the spring. Alright? So how would we do that now? Anybody have any idea? Yes, good afternoon, Stefan. Can you hear me? Oh, disconnected. Yes, Stefan, can you hear me? All right, so we have this question right here. Anybody have any idea as to how we could approach this question if we want to know the force that is applied to the spring? Anyone have any idea how we could approach this question? So notice that, we have a seesaw, well, a plank, and we have a pivot. So once we see this plank and this pivot, which concept we can start to consider? Which concept we can consider in this question? Anybody? Anyone has anything? Sharon? Sharon?
Say, the scroll up, sir. Scroll up, sir.
Wait. Let's just work on this. I'm gonna give you a chance to get information from up top. So here we are, Desmond. How would you approach a question like this? Huh?
So it would be KF equal KE, right? We'll be using that formula.
All right, so let's start with that. So let's start with somewhere. So we say F is equal to
KE.
KE. All right. Now, what is K? What's the value of K? Do we know the value for K?
K is Newton. No, we don't know the value for K.
Right.
Wait, K? Oh, yeah,
Yes.
we do.
What's K?
No, we don't know the value for K. We don't know the
Right.
value for K.
So K is unknown.
K is
Right? What's E?
unknown.
What's E? What's the value of E?
The E is 0.8. Wait,
No, man.
calculate
Different question.
this.
Different question.
Applied.
now.
Oh, 4 meter.
Wait. E is the extension of the spring. Do we know the extension?
Yes. Oh, no.
No, we do not.
No, we do
Right,
not.
so this is also unknown. But look
So how
at the
would you
setup
work
right
with
here. Look
that?
at the setup. What does this remind you of?
The moments, the seesaw.
Moments, right? So we can consider moments because if we look closely, what we're going to see is that we're going to have the weight producing a moment in this direction, which we refer to as a clockwise moment. Yes?
Yes.
Right? Well, at the same time now, we're going to have a moment due to the spring in this direction and refer to that as a anti-clockwise moment. Agree?
Agreed.
Right? So we have a clockwise moment, and again, this clockwise moment is about the pivot, and this anti-clockwise moment is also measured about the pivot. So let's say we consider that first of all. So since we're looking at moments, we're going to consider the principle of moments because we're indicating that this system is in equilibrium, and once we have a system in equilibrium, we can consider the principle of moments. So by the principle of moments, we can say that the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments also about that point. So in this case, now we have a clockwise moment due to the weight of this plank, and we have an anti-clockwise moment due to the force along this spring. So now, we can now write that our clockwise moment, let us say we consider this one to be F1, right? And the force right here, we're going to consider it to be F2, right? So what we're going to see now is we can write that F1 times D1 is equal to F2 times D2. Good so far?
Understood.
Okay. Now, we can now start to substitute values for F1, D1, F2, and D2. So F1 now is 500 newtons, as we have right here. D1 now is the distance from the line of action of F1 to the pivot. So because this is 4 meters long and it is uniform, we expect the center of gravity to be located at the center. Agree?
Agreed.
Right? So because this is a uniform plank, the center of gravity is going to be at the center. And if it is 4 meters long, we expect the center to be how far from this end would the center be? Let's say we call this A, right? And this one B. How far from A would the center be? Huh? If we have a 4 meter long plank and we have the center located right here, how far from the center would A be? What would be the distance from A, one end?
Would it be 2 meters?
2 meters. Everybody agree?
Yeah.
Stephanie, you agree? Stephanie, let me know if you're hearing me.
I agree with myself because I know for a fact that if it's in the center and it's going to one end to the other, it should be half because it's in the center.
Right, right. So it would be from here to here would be 2 meters. Now, the pivot is 0.8 meters from A. So what would be the distance from the pivot to here? What would be this distance from the pivot to the center?
3.2? No,
Huh?
no, no. 1.2.
Right, 1.2 meters. So D1 then now is 1.2 meters, and that is equal to F2, which is an unknown value, multiplied by D2. Now, the spring is attached to the end at B. So what would be the distance from B to the pivot?
3.2.
3.2. Right, so let's say now this is 3.2. 3.2 what now? Meters, right? Because it's the distance, so 3.2 meters. So now we can start to simplify here. So 500 times 1.2, what does that work out to? So if we say 500 multiplied by 1.2, what we get?
600.
right? So this becomes 600 Newton meters, and that is equal to F2 times 3.2 meters. Now to find F2 now, we could divide this one by 3.2 meters and also divide this one 3.2 meters. Now simplifying, I'm going to put F2 on the left hand side. So F2 then now becomes 600 Newton meters divided by 3.2 meters. And what's the value we get for this one?
187.5.
So let's say probably 188. Can we say 188?
Yes, sir.
Yes, because you round up.
All right, so let's say we round up. So 188. And this is what now? So meters cancels with meters, so we're going to get 188 newtons. So the force being applied to the spring is 188 newtons. All right, everyone okay with this?
I understand.
Yes,
Okay.
sir.
Okay. So Desmond, you follow this thing a while ago? Desmond.
Yes, sir. I'm following.
Okay.
Sir.
I'm still gonna scroll back up. I just wanted to cover this before we move on. So that would be the
Okay, sir.
force applied to the spring. Now let us say we say all right. Let's say I add a second question. I will say for this one now we say let us say the spring constant of the spring is, could somebody give me a value?
One point two.
1.2. So let's say I use 1200 newtons per meter, right? Newton per meter. That's the spring constant. Is 1200 newton. Calculate the extension of the spring let's say in centimeters, right? Just a little challenge at the end right here. So this now, we can now apply Hooke's law. So we can say F is equal to KE, because now we know the value of F. We said F was the force along the spring, which is the 188 newtons. We know the spring constant K, which is 1200 Newton per meter, and we're trying to find what now? We're trying to find E. Right, E, yes. So we're trying to find E, which is the unknown. So now, rearranging this expression right here to make E the subject, divide this one by K, divide this one by K, and we get that E is equal to F divided by K, which works out to be F is 188 newtons, and this is 1200 Newton per meter. And plugging this into a calculator, we should get a value of what? Anybody know what this is? Anybody know what this is?
0.1.
0.156, but if you round it up, I guess it will be 0.157.
So let's say with a two decimal place, or two sig figs.
So 0.16 if you round it up.
Right, so 0.16 meters. That would be the extension. Now, quick question. What would be the new length of the spring if the original length was 0.2? Original length was 0.2 and the extension is 0.16. So what would be the new length? What?
0.32.
Well, remember it was 0.2 and this is 0.16.
0.18.
0.36.
0.36. 3/6, right? So the final length, LF, is going to be the extension plus the original length. So the extension we say was 0.16 meters and the original length was 0.2 meters. So adding these two together we get 0.36 meters, but again we still want it in centimeters, right? Or actually extension in centimeters. So what I would have to do here is divide this by 100 and get 0.0, no, well, sorry, my bad. Not divide by 100, multiply by 100 because I'm going from meters to centimeters. So I multiply by 100 and I'm going to get 16 centimeters. Okay? So this would be the extension in centimeters. All right? Are we okay with this?
Yes, sir.
All right?
Yes, for the most part, I get it.
Yeah, we're having problem.
No, I understand it, but I might forget a few things, so I need to practice. That's it.
Okay, so it's just a matter of applying the concepts of moments, right, to determine the force acting right here. Just like the example with the bicycle. So this would be like a string holding up this section. So there's going to be a tension, right, along this spring, right, which will be supporting this plank and it will produce a anti-clockwise movement about the pivot. So did we get a chance to take down this information? Because I want to scroll back up top. We got this information down?
Yes, sir.
Okay.
Yes, sir.
All right, this was what you wanted to say. Where was it? Up here? Desmond, where did you miss?
So right before we started, like the right when you start drawing the beam, right before there.
Oh, so it's
So
right.
like right here, yes.
Yes, it's right here, right here. So Stefan, if you're hearing me, let me know. Confirm, thumbs up, thumbs
Yes,
down.
sir, I got the screenshot. I got the screenshot.
Okay. You following what's happening so far?
Yes, yes, sir. I'm following.
Okay. All right. So that I want to give you a few questions to try. All right. So let me just give you guys a few questions, and I want us to together go through a graph question. So in the meantime, you can get your graph papers together. I want us to plot a graph together on this topic. Let me just let's go here. So let's say a few examples. So let's say activity. So let's say question 1 right here. Let's say calculate the force applied to a spring of spring constant 2640 Newton per meter if it extends by say 0.08 meters. All right, so that's question 1. Question 2 now. A spring is fixed to a ceiling and a weight of, let's say this is probably 80 newtons attached to its other end. To its other end. What extension would the 80 Newton weight produce if the spring constant is 240 Newton per meter. Let's say now we add another one and we say find the final length of a spring of length. Let's say the length is say 10 centimeters. Let me say 12 centimeters. So 12 centimeters when a say a 4.2 Newton object is attached to it, given that its spring constant is, let's say the spring constant is 25. Let me just say yeah, let me try it. Let's say 25 Newton per meter. Let me write it like that so you guys can be aware that sometimes we can write the spring constant as that, the unit as Newton per meter. So think I'm going to add two more. So can I scroll past question 2? Can I scroll past question 2?
Yes, you can.
Okay. All right. So let's say for number 4 now. Let's say a mass of
I didn't get to finish right of number 2, sorry.
a mass of let's say this mass is 20 kilograms is attached to a spring so that it extends, so that it extends by 0.52 meters, which is a whole heap of extension. Let's say 0.052, right? Meters. Calculate the value of the spring constant of this spring, right? So that's that. And let's see now, let's see if I make this question 5 a diagram question. So let's see question 5 now, gonna be a diagram. So let me just set up the diagram in the meantime. So let's say we have this. So we have that. We have a spring, like so. So that's the spring. And let's say now we have same thing here. But the spring now is now affected.
Go back up, Sarah, please.
Okay, give me a second. Let me just put this together first. So let's say this is what we have now. Let's say this is 60 newtons. Let's say this one here is, say this is probably say this is probably 8 centimeters, and let's say this one now. So I'm going to say this one is say this one is 15 centimeters, right? And let's say now for part A, we say calculate the extension of the spring in, we'll call this again now, in meters. And then B now, we're going to say now find the spring constant K. Let me see this now. And then now, let's say now C, or what would be the new length of the spring if a 100 Newton weight is attached to the spring. So what we're saying is that if we were to remove the 60 Newton weight and attach a 100 Newton weight, what would be the new length? So let me go back up for those who miss, and then I'm going to come back out here. So this is where we are. Is this good for anybody? Or for everybody? Did anyone want to see right here? Let me know. Okay. So these are the 5 questions. So I'm going to give you guys 10 minutes to complete them and submit. So I'm going to create the assignment for you to submit, and then we're going to move on with looking at the graph. So ensure that you have your graph papers ready, so we can talk about this graph question. Maybe we go over into looking at it as an assignment, but I'm going to allow us to start working on it, and then we continue. Well, then you guys will actually be able to finish it up.
I'm on the last question.
Okay, I'm gonna give you a few minutes to complete, and then will move. Is there anyone who is having any challenges?
I'm having problems with the last question.
Okay. What problem in particular you having?
So we replace the weight, the 60 Newton weight with the 100 Newton weight, right?
Yes.
And so our known values would just be F equals to 100 Newton weights, and we wouldn't know anything else, right?
Well, you would have calculated the value for K, so that
And
value.
so we'd use that to find the
Right.
extension.
Yes.
Okay, I understood.
So I'm assuming everyone else would have finished.
Junior, could you scroll back up to the first question, please? Thank you. You can scroll back down.